Hello! In this video, we'll analyze the performance of the multicycle processor. So in the multicycle processor, different instructions take different numbers of cycles. Branch on equal takes only 3 cycles. R-type instructions, add I, store word, jump and link all take 4, and load word takes 5. So the number of cycles per instruction is the weighted average of these. If we consider some application, for example, the Specint 2000 benchmark was a benchmark for measuring performance of computers. About 25% of the instructions in that benchmark were loads, 10% were stores, 13% were branches, and the remaining 52% were R-type data processing instructions. So the average number of cycles per instruction is 13% being 3 cycles, 52 plus 10% being 4 cycles, and 25% being 5 cycles, so on average it's just over 4 cycles per instruction. Next we need to look at the cycle time of the processor, and there are various different cycle times that might be limiting. So let's look at 2 of the ones that seem like they could be longest. One of the steps starts with a program counter and goes through the ALU. So PC, we need to select source A. We need to then put that through the ALU. We get a we get PC plus 4, and we need to select that PC plus 4 with the result multiplexer and bring that back around. So we'll call that the blue path. In the red path, that's the delay reading memory. So we'd start with an address and ALU out. We would choose that address with the result mux, bring that address around, choose it again with the address mux, and access that data memory, read it out, and we need to put it into the data register at the end of the cycle. So let's make some assumptions. One of them is that the register file is faster than accessing memory, which makes sense because it's smaller. And another is that writing memory is typically faster than reading memory. So if those assumptions are true, then the store write path to memory is not a limiter, and the paths accessing the register file are not limiters. So the worst case cycle time for the multi-cycle processor is the time to come out of the first register, plus time through the decoder, plus time for 2 multiplexers, plus the maximum of the time either for the ALU or to access memory, plus time to set up at the next register. So if we put in these values, the time through the first register is 40 picoseconds, the time for the decoder is 25 picoseconds, 2 multiplexers is 60 picoseconds, longest of the ALU and the memory is 200 picoseconds, and the setup time is 50 picoseconds. So this looks like 100, 200, 250, 275 picoseconds. Check my math, 100, 300, 375 picoseconds, which is about half, in fact it's exactly half of what the single cycle processor had been. So this is definitely faster cycle time, but got to be careful, it's only twice as fast, and now we're taking between 3 and 5 steps to do each instruction, so we may not be getting a speed up. So if we consider a program with 100 billion instructions, that's 10 to the 11th times 4.12 cycles per instruction times the cycle time of 375 times 10 to the minus 12 seconds per instruction. That will give us our overall execution time, which I don't have in front of me, but it's going to be about twice as long, something a little over 150 seconds as compared to 75 for the single cycle processor.